Hi, I'm Chuhan Zhang, a PhD student from VGG Oxford. I'm going to present adaptive text recognition through visual matching. This is a joint work with Ankush, Gupta, and Zisserman. Our objective is a text recognition system that can generalize to different visual styles, adapt to different languages with a flexible number of classes. Traditional text recognition normally follows a common pipeline as shown in the figure here. It has an encoder for embedding visual features and a decoder which maps the feature into predictions. However, it has three main limitations. First, it requires a large number of fonts and textures to generalize well. Second, it is only being able to do classification over a fixed number of classes. Third, it is not transferable to new visual styles without retraining the entire network. In our work, we cast text recognition as visual matching, giving a text line and a set of glyph exemplars. By glyph, we mean character shape. We compute a similarity map to find correspondence between the elements in the two input images, thereby recognizing the contents in the text line. Text in other languages can be easily recognized by providing a different set of glyph exemplars without needing to fine-tune the network. By visual matching, we overcome the following limitations. First, it relieves training from learning specific visual styles. The training is not limited to a certain alphabet. Instead, random shapes and patterns can be used to learn a better representation for visual matching. Second, the similarity map is agnostic to the number of glyphs. It allows us to recognize different languages with different alphabet sizes. Last, the similarity map disentangles the encoder and the decoder. It acts as a bottleneck and interface in the model, leading to flexibility and generalization at both ends. Our visual matching can be seen as one-shot sequence recognition, which is a more general problem than one-shot image classification. In one-shot image classification, given the exemplars and the image to be classified, the model only needs to find the best match. While in sequence recognition, we need to both segment the sequence into instances and also classify them. Now we explain how the model works. The model has a similarity map bridging the encoder and decoder. The encoder extracts visual features for computing a similarity map. The map is then enhanced and analyzed by the encoder to output a line prediction. Let's look at the encoder first. Two unsegmented line images are input into two identical encoders. Feature vectors from the encoders are used to compute a cosine similarity map. Here is an animation showing how the map is generated. The visual feature from the first patch in the text line image is compared against all the visual features from the glyph line image, outputting the first column of the map. As the window sliding across the text line image, more and more columns are computed. At this stage, no segmentation information is provided. The size of the map is proportional to the width of the two input images. Then the map is passed into the first stage of the decoder. This stage is designed to remove the ambiguity and output an enhanced similarity map. Apart from it, the XY position encodings and a ground truth glyph width matrix are also input for instance segmentation. The ground truth glyph width map has the same size as the similarity map, with bands labeling the width of glyph exemplars. All the input maps are stacked to be a tensor with 4 channels and supplied to the disambiguation module for an enhanced map with higher contrast and less ambiguity. The second stage of the decoder is the classification stage, where the enhanced similarity map is decoded into a probability matrix over the alphabet. Another glyph width map is input into this stage to aggregate the similarity map into classes. It is a binary map with number of columns equal to the size of the alphabet. Each column corresponds to a glyph exemplar. In each column, pixels at the same height as its corresponding glyph are set to 1. When we multiply a single column in a similarity map by the glyph width map, it gives a probability distribution over all the glyph exemplars. Therefore, in a class aggregator, we apply matrix multiplication on the two embedded maps to compute the final probability matrix. This is the full picture of the model architecture. In training, first we sample a text line from the synthetic training data, and then choose glyph exemplars from a random visual style to carry out the visual matching. The glyph exemplars are stacked to be our glyph line. We have two losses for training. The first is an auxiliary loss aimed at training the visual similarity encoder. It is a cross-entropy loss directly on the columns of the similarity map. The second is an conventional CTC loss on the decoder for aligning the dense predictions from the similarity map and the ground truth string. We evaluate our method on 4 different tasks. First, generalization to unseen fonts with limited training data. Second, generalization to real data of models trained on synthetic data. Third, from English to other Latin languages with similar shapes but different alphabet size. Fourth, from English to non-Latin languages which are different both visually and in the alphabet size. We evaluate generalization to novel fonts using a synthetic generated dataset we introduce called font synth. To construct font synth, we use fonts from MJ synth dataset and divide them into 5 categories by their attributes. Fonts from attributes regular, bold, italic, and light form the training set, while fonts out of the 4 attributes form the test set. We train our model and SOTA baselines with increasing number of attributes from 1 to 4 and evaluate them on the novel test font. This chart shows a comparison with the SOTA OCR method from 3 diverse domains: syntax, document OCR, and handwritten text. For a fair comparison, we first compare under the setting where the test font glyphs are not assumed to be given. Instead, the best matching training font is selected automatically based on a confidence measure of the similarity map. When training with only one font attribute, the regular font, we outperform the best SOTA baseline by about 6%. As the training data increases, the gap between our method and the SOTA baselines is reduced, but our method still has the lowest error rate. Hence, our method is more accurate than existing method, especially in low training data regime. Since our method is based on visual similarity, we can train with data other than the target language. Hence, we further train our model on text lines using the glyphs from a mini-glot dataset. It significantly reduced the error by about 40%. Finally, we evaluate our method in one-shot setting, assuming access to font exemplars present in the text image. This reduces the character error rate significantly, demonstrating the strong generalization capability of matching-based method. Next, we test generalization to real data of models trained only on synthetic data. We consider 2 settings. First, we take models trained on synthetic English images and evaluate them on real English images from the Google 1000 dataset. Second, we go one step further and evaluate on real data from other Latin languages with additional accented characters, also from Google 1000. Further, the real dataset poses significant challenges due to degradations, ancient typefaces, as shown above. Our method outperforms the SOTA method both for English and other novel languages without any fine-tuning. Finally, we demonstrate generalization to completely different non-Latin languages sampled from the omniglot dataset. For more details of these experiments, please refer to our main paper. In the end, we present some visualization of the similarity map computed from different datasets used in our experiment. More examples and visualizations can be found in our supplementary materials. Thank you for watching. Code, pre-trained models, and dataset can be downloaded from our project webpage.